Okay, thank you very much to the organizers for inviting me. Should we close the door, maybe? Okay, so first a comment. Under this web address, which has the typical German starting point, www.math.uni-hamburg.de/home/my name, then FL script, where FL stands for city, and script is unfortunately written with a K. That's a German error. You can get lecture notes. They will be updated. And if you look at the lecture notes, you will see that for a long time, the word skein theoretic will not be mentioned. The reason is that in order to understand CFT correlators, and you will say, aren't these some complex functions with interesting properties? In terms of skein theory, you have to build a big bridge. And maybe 2/3 or even 3/4 of the lecture will be devoted to bringing you to this point. So please be patient and let me develop the subject. So let me give you an overview. So the first thing is the skein theoretic constructions need as input certain categories. So these categories are categories of representations of so-called vertex operator algebras. So I need to tell you something about this, that you know what these categories are. And actually, these categories have a lot of structure. And I have to tell you at least a little bit what this structure is. So I will have to tell you that these representation categories are actually braided monoidal categories. And they have a nice duality structure. In general, they are so-called Grothendieck-Vertier categories. We will not work with Grothendieck-Vertier, but I will mention this at least. They get these properties from conformal blocks. And conformal blocks have a twofold role in this setup. Conformal blocks are on the one hand side the building blocks of correlators. So I have to explain what they are if I want to talk about correlators. On the other hand, the structure of conformal blocks will precisely impress this additional structure of braided category, actually a ribbon category, and these duality structures on the category. So we better have a minimal understanding about them. And then in the last part of the talk, I want to do a skein theoretic construction. And since the director told us that here interaction between different fields is important, let me say that these type of constructions also arose in condensed matter physics, and they are called string nets. The word string here is not directly related to string theory. Yeah? So I will explain this and then in the end explain how you describe correlators in this setting. So my first chapter is about some very general comments. The first thing is, if you talk about two-dimensional TFT, and this is always CFT, and CFT will be always two-dimensional. This is not because there's nothing interesting to say about CFT in higher dimensions. That's because I have today and tomorrow nothing interesting to say about them. And now there are two different types of theories. One is what I want to call chiral CFT, and the other one full or local CFT. Both are important for physics. Both are rather different. Let me start to say on which kind of geometry they are defined. Two-dimensional local CFT is defined on two-dimensional conformal manifolds. Well, a conformal manifold is a manifold with a metric, but the metric only matters up to local rescaling. So here I'm talking about a metric. So I should say metric of what signature? Some of you in the audience will expect maybe a Lorentzian signature. Some of you will expect the Euclidean signature. I will talk in these lectures about Euclidean signature. This doesn't mean that there are no results about your Lorentzian signature. There are actually surprisingly similar structures appearing if you investigate Lorentzian signature. The fact why these same structures appear is not completely satisfactorily understood. At least I haven't understood it in a sufficiently satisfactory way. Why Euclidean signature? Well, there are several reasons for this. This is a theory which arises in the description of critical phenomena. This is the theory which arises as the worldsheet theory of strings. And now I'm a bit sloppy in what I call manifolds, conformal manifolds. Well, actually we will talk about conformal compact manifolds. And if you think about strings, there are string theories with oriented worldsheets, string theories with unoriented worldsheets. I could talk about both cases, about the construction of correlators. I will assume that this here is oriented. If you want to get information about unoriented strings, which appear in string theories of type 1, unoriented CFTs, please ask me questions. What we will do here is we will talk about, well, not only two-dimensional manifolds, which you, compact manifold, you might imagine it as something like this, but we will talk about, ultimately, about stratified manifolds. What do I mean by this? In physics parlance, I will talk about CFT in the presence of defects. So by this, I mean that there can be line-like structures which separate two TFTs, which are different, and of course, there has to be about a condition, a boundary condition, a defect condition. And then these defect lines, they could even branch, so there could be finitely defects, many defects running into a point. You might wonder, what are the field insertions here? Well, defects will be always topologically defects, so the position doesn't matter. We can move them a bit, and the correlators will not change. This doesn't mean that there are other interesting defects. That's what we deal with. Defects were rather exotic when we studied them first more than 20 years ago. I think these days there are people in the string theory community talking about a symmetry revolution, where it becomes more and more acknowledged that codimension 1 defects are a nice way to incorporate symmetries of a theory, or higher codimension defects have a role to play. By the way, since the director was saying this, sometimes developments take a lot of time. When we wrote for the first time about topological defects in 2000, without any 20, in 2000, people were not interested in this. And this is a hard fate for a young scientist, so I have some pretty clear idea what many of you are in, what kind of situation. Okay, good. But anyway, sometimes things turn out very well. Now there's another type of CFT, chiral CFT. There is the following fact. If you're in 2 dimensions, a conformal structure plus an orientation is a complex structure. So the manifold becomes a complex manifold, a complex one-dimensional manifold. This is not the same geometry, right? So here we are working in with complex one-dimensional manifolds. That's why one says complex curves or Riemann surfaces. You can say this in whatever way you want. And here, this is necessarily oriented. So here, the theory might be orientable, but no orientation chosen. Yeah? Here, an orientation is chosen. This is a theory which is important as an input to understand it, but it has also physical applications. The physical application here is in the realm of quantum Hall physics. If you want to describe universality classes of quantum Hall fluids, well, you can use here structures appearing in chiral CFT. And the orientation in quantum Hall physics is a very physical thing. It's a magnetic field which distinguishes one orientation over the other. Yeah, so it's not true that one is physical, the other is not physical. So now here we will have to deal with symmetry structures, and actually as symmetry structures I wrote here VOA, which are vertex algebras. This is not the only formalization of symmetry structures in the CFT. So there are different formalizations. For example, you could work with something that's based on C-star algebras. This approach builds in unitarity very deeply. We do not want to build in unitarity, and there are several reasons for doing this. Let me be honest, my first reason is this forces you to work with much clearer mathematical tools, and I'm simply interested in this. A second reason is that for certain applications, you do not have unitarity. If you go to critical phenomena like critical percolation, then the theory is simply not unitary. And we are only getting close to saying something about CFT from algebraic points of view for phenomena like critical percolation now, although this has been promised since the 80s when probably most of you were not even born. Yeah, so, okay, so that's, I'm also not going to talk about the construction of CFTs from a Lagrangian. So there is a gap. So Peter Bauknecht will talk about structures that can be used to describe CFT Lagrangians, higher structures, gerbs. Of course, going from a Lagrangian to a quantum theory is not a process that's necessarily well defined at all steps. Again, there is some intriguing fact that if you study gerbs, you will find structures that are appearing here in this algebraic approach. You find an analog in gerbs. So for example, if you want to describe CFTs in terms of gerbs on unoriented surfaces or on surfaces with boundaries. But, well, maybe this Peter is not here, I think, but we can do this in a ping pong of questions after his or my lecture to elucidate this. For the moment, let me go further. So actually, here, what we want to understand ultimately is what is the system of conformal blocks, and they will be described in the end, or properties of them that we need to control to construct correlators will be described in terms of a notion that is called a modular functor. On the other hand, here we need to define what does it mean to have a full CFT, and there the crucial notion will be the notion of a consistent system of correlators, and I'm trying to give you definitions of this in the course of this lecture. And skein theoretic methods precisely serve to select such as this consistent system of correlators. Okay, so you see I talked already a bit about two-dimensional geometry. Is there a way to keep this microphone a bit more stable? I mean, probably I'm moving too much, or my ear had to grow. Yeah, you can also fold my ear.
This way is quite stable.
Okay, good. Yeah. Alberto, please ask a question. Yeah. Sorry, but I will, if I see next time the impression on your face, I will ask you to ask. Okay, so I want to explain you this relation between complex curves and two-dimensional manifolds in a way that makes contact to something John was mentioning earlier in his lecture. So suppose we have so what was John's idea? What he showed is that a geometric object, and let's take simply the complex affine plane, can be described in terms of an algebra. I'm very simple-minded. I take as the corresponding algebra the complex polynomials, right? And if you have heard some algebraic geometry, you will know what I mean by this. Otherwise, simply take it that the roots of any complex polynomial decomposes into linear factors, and a linear factor is described by a complex number, and that's a point in here. Let's now describe what should be real affine space. And you will say, oh, come on, that's a line. But that's not really true. We do the same logic. We take an algebra of functions. And now remember from non-commutative geometry that a complex point is a map into affine space and into complex affine space. And if you go to the algebras, you turn around the direction. So you go from the polynomial ring and you look at the ring homomorphism. This is the structure we had this morning, okay? And in fact, that's what polynomials are made for. Well, they are made to plug in numbers and to produce a ring homomorphism. And that's their universal property. Now, what should we do here? You will say, okay, we should do the same and we should plug in real numbers and get the real numbers. But well, polynomials are not made to plug in really the ground field, but if you have polynomials over a field K, you are allowed to plug in any K algebra. And what is another important K algebra? What is another important R algebra? This is find homomorphisms, ring homomorphisms into C. And of course, that's what we do in a plain language. Here, we take a polynomial and we put in a real number R. But here, well, we can take a complex number and send the polynomial to f of alpha. And you will check if you plug in the complex conjugate, you're getting a ring homomorphism which is equivalent. Well, what does it mean? The points here you have are really secretly not only the real line, but it is the upper half plane and the lower half plane identified. So think about here this geometry as something which has a boundary. These are the real points, and which has points in the interior. And this is a systematic way to get in a real setting something from a complex setting and a Z2 action. Well, that's the action of the Galois group. And of course, you have been using this, if you are a physicist by training, you've been using this in electrodynamics, right? The method of mirror charges is exactly doing this. Yeah. So what I want to motivate in this way is that if you are interested in full CFT on a conformal surface sigma, you should study a twofold double. You should study sigma hat, that's a double, which I call the Schottky double, which can be constructed in a completely systematic way, generalizing this idea, but which can be done explicitly also as follows. Let's do examples. So, if the idea is, if sigma is a disk, take all points in the interior and double them. The points on the boundary do not double them, but glue together the two copies at the boundary. So what is the double here? Well, the double is really a sphere. Well, it is not the sphere. It is really the sphere plus the reflection at the equatorial plane, which is an anti-holomorphic involution. Anti-holomorphic means it respects the conformal structure, but it reverses the orientation. Well, let's do some other example. Let's do, for example, an annulus. I'm drawing the annulus deliberately in this way. I do the same thing, I double it and I glue it together. So here the double will be something which looks as follows. Sorry, these are two annuli glued together in this way. What is the double of a Klein bottle? Who has any guess? Well, I have to double the Klein bottle. Yeah? And now, if you want to get an easier guess, you might remember from elementary courses on two-dimensional compact manifolds that there's the Euler characteristic. Okay? The Euler characteristic is 2 minus the number of handles minus the number of boundaries if it is oriented. If it is unoriented, it is minus the number of cross caps. So what is a cross cap? Well, let's take such a surface. How do I get a boundary? Well, I take a pair of scissors and I cut out a disk. How do I plug in a cross cap? I'm cutting out a disk and I'm identifying antipodal points. Then I've inserted here what people call a cross cap. You're familiar with this if you're constructing real projective space. Real projective space is the upper half disk with opposite equatorial planes identified. Yeah, so that's and now for the Klein bottle, we have an Euler characteristic, which is here 2 minus no genus minus no boundary and actually 2 cross caps, so it's 0. Now, if you are bored or if you're looking for something else, then I ask you to solve the following exercise. It's not an official exercise of the course. If you take a surface and you plug in 3 cross caps, yeah, so you cut out 3 disjoint disks, you glue them with antipodal identification. It's the same as increasing the genus and plugging in 1 cross cap. Do this as an exercise. If you're able to do this, you've understood everything about the fundamental group. Yeah, so anyhow, the Klein bottle comes with 2. So the Euler characteristic is 0. Now, the Euler characteristic can be obtained by integrating something over the space. If I'm integrating something over a space which is twice as big, the Euler characteristic will, as an extensive quantity, will double as well. The double of 0 is 0. So it must be a surface of Euler characteristic 0, but that's the torus. And indeed, the Klein bottle comes. If I take a torus, let's identify this line, and let's identify this line. And as a Z2 involution, I take the point here to the point here. So if I go here to the right, I go to the left, and I'm going upstairs. This is a fixed point free involution. Yeah? And again, if you want to see many of these pictures how to double this in an algebraic geometry context, go to the Red Book of Varieties and Schemes, and you'll see exactly the pictures you find in string theory papers. Yeah, so anyhow, we have this doubling procedure. I have already talked about some topological aspects. There is another topological gadget which I should introduce very early, and which will be very important in the sequel, and this is the mapping class group. So mapping class groups, and well, maybe this is a general disclaimer. I'm now mentioning many things. These are important subjects of mathematics, both classical and of ongoing research. And I'm not an expert for them, I'm simply mentioning facts. But these are facts you should keep in mind when you want to understand why ultimately we are talking about CFT correlators. Good. So what do? We have a topological surface sigma, and now we can consider homeomorphisms of sigma to itself. And we have to be a bit careful. If sigma is oriented, then I will consider orientation preserving homeomorphisms. If sigma is not oriented, obviously I will consider all homomorphisms. And now it turns out that there are homomorphisms that can be continuously deformed to the identity homomorphism. This has to be proven what it means, because I simply told you, these are continuous maps from sigma to itself, which are bijective and which have a continuous inverse. You have to put a topology on this and to say what it means. They can be continuously deformed. Then you can talk about the connected component. So those that can be, of those homomorphisms that can be deformed to the identity, and it turns out to be a normal subgroup. So this thing is, in fact, a group, and that's what's called the mapping class group of sigma. Now, to give you some piece of information about a mapping class group, if we take sigma to be oriented and no boundary to make life simpler, then we can study how does the first homology, and say homology with values in Z, how does it behave? Yeah? So this is represented, to give you an intuitive picture, this is represented by things that are called in the literature A cycles and B cycles. So really, if you choose a base point, there will be a class of cycles going like this. There will end like this, one for each handle, and there will be cycles which go in some other way. From the same base point, they will go from here, they go around, and they come back. And it turns out that this here is a 2G-dimensional vector space, which has the thing everybody hopes for, a 2G dimension. So, sorry, it would be a vector space if I had taken coefficients in a field, a 2G, a Z module of rank 2G, and it comes with a symplectic form. And it turns out that the mapping class group action is compatible with this symplectic form. So this means that if we take the symplectic group with integer entries, because the whole structure is integer, then this mapping class group induces something which preserves the symplectic form, and it can be proven that this is a surjection. In general, for general G, well, no reason why it should be an isomorphism, but for the very important case that sigma is a torus, it turns out that this is an iso, and the mapping class group of the torus is SL2Z. SL2Z is also symplectic, the symplectic group. Okay, so we have here our mapping class group, and for the moment it is simply something that's there and that I'm going to use a bit later. Now, I talked a bit about complex geometry. Let me next talk, about topology. Let me talk about complex geometry. I have already mentioned quite a few things in the introduction. What I should maybe add here is a very important case. I did here simple examples, but what happens if sigma is an orientable surface? What is in this case the double? An orientable surface without boundary. Well, I have to only interior points, I have to double them. So in this case, I get sigma with one orientation, disjoint union, sigma with the other orientation. This is very geometric. Yeah, so you take simply for every point, and it's in every orientation you take a point in a twofold cover. An orientation of sigma, by the way, would be a section in this bundle. Well, what you see is if we are interested here and choose to describe CFT, and we choose a local coordinate, we will get two local coordinates. Suppose we have already fixed an orientation, you will get two coordinates here, z and z star. And this is actually a geometric way to take into account what's frequently done in CFT, that one says sometimes I'm dealing z and its conjugate as the same, and sometimes not. If I'm not dealing with it as the same, I'm typically interested in chiral CFT, and I'm working on the double where these are two coordinates. If I'm identifying the two, then I'm interested to work on the quotient, and I require that these two coordinates are related by the anti-conformal involution, sigma, because always the double comes with an anti-conformal involution. Good. Let me just check, because now if we go to complex geometry, then it's a famous fact that if you take a generic manifold, closed-oriented two-manifold, the complex structure is not unique. What is a complex structure? You want to find an atlas. An atlas has charts going to R2. You consider R2 as C, and you want that the change between different charts is biholomorphic. And you can do this in various ways. So for CFT, this is a very important feature, that you have different ways, different conformal structures on one and the same topological surface. Let's try to be a bit more specific. So the first thing is, I claim that the homomorphisms act on the conformal structures. Why do they act on the conformal structures? Well, if you apply a homomorphism and then you say, then you will get a different, oh, let me write down something. I should. You see, now I feel really abroad, because this is dry cleaning. Anybody who has been in Germany knows why. Okay, good. So what you can declare is that a complex structure on a given curve, well, let me call it sigma hat because I have the double in mind. I define a complex structure here, given a complex structure here, so these are complex structures, by declaring that this map, which is an orientation preserving homeomorphism, so it's not holomorphic for one structure, but that this becomes holomorphic, so I'm changing exactly the structure in a way that it becomes holomorphic. In this way, the homomorphisms act on the space of holomorphic structures, and there is a famous space for a surface which is called Teichmüller space. And Teichmüller space is the space of all holomorphic structures modulo the action of homeozero, so those in deforming to the identity. So the point is here that Teichmüller space and Teichmüller theory is again a very active field with lots of important results. This is a complex manifold. It's naturally a complex manifold. If you want to know example, in genus 0, it is just a point. So on the sphere, nothing happens. But for genus 1, well, we have to deal with the torus. And in this case, Teichmüller space is the complex upper half plane. Yeah? So that's the way to see the complex upper half plane. And in general, one can show that Teichmüller space is isomorphic to this space with some complex analytic structure, but in general it is not as a complex manifold isomorphic to what you would expect, C to the 3G minus 3. Yeah? So that's in general not true. Now, the important point for us is, and that's a deep fact, that Teichmüller space is simply connected. Now, simply connected means the fundamental group is trivial. But why is this important? Because to say it in a very informal way, there are no non-trivial bundles over Teichmüller space. So if you are interested in studying vector bundles, they will be trivial over Teichmüller space. Conformal blocks will be vector bundles, which lead to vector bundles over Teichmüller space, and as such, they will be trivial. Yeah? So this will be an important aspect here. Now, the point here is now that we can go one step further, and I don't want to erase this because we have here a quotient. And so far we divided out on all complex structures only as this subgroup, but if we now divide out on Teichmüller space, I call this T, on T of sigma, the induced action of the mapping class group of sigma, then I'm getting really the moduli space of inequivalent conformal structures. And this is quite important because this is the importance of the mapping class group. If you had an elementary course on, well, whatever elementary means, on string theory or CFT, you've probably seen one example. And this is the example which I take by combining the things that are here on the blackboard. So we have H1. This is the complex upper H plus, the complex upper half plane. The mapping class group is this. So we should get an action of SL to Z here. And in fact, this is a famous action. So a matrix ABCD here acts by sending this to AZ plus B divided by CZ plus D. And so when I told you that vector bundles over Teichmüller space are trivial. If I'm interested to study vector bundles over moduli spaces, then they will form representations of the mapping class group. So that's why, in the end, talking about representations of mapping class groups is absolutely essential. Yeah. So these are things I wanted to settle here. And before finishing this quick chapter on two-dimensional geometry, well, maybe I should do this action explicitly to recall things you have seen before. If this is the upper half plane, then the modular group has one generator which sends z to z plus 1. This corresponds to 1, 1, 0, 1. Well, this allows me to restrict to a strip between 1/2 and 1/2. And it has another generator, z goes to -1 over z. I think many of you have seen this, well, which allows me to restrict here to a fundamental domain, which is here. And what you learn is the correct way to think about the fundamental group of this, this fundamental domain is that this is really the mapping class group SL2Z. Why is this correct? The fundamental group doesn't act fixed point free, so there are fixed points here, and there is a fixed point here, which is, of course, the same as this one. Yeah? And then you have to work with the appropriate notion of fundamental group. That's an orbifold fundamental group, and I think I have given you in the lecture notes references about this, how to compute orbifold fundamental groups. Yeah? And what is, by the way, quite interesting is the point here at infinity, at I infinity. That's what's called the cusp. What happens for a curve if I go to this point I infinity? Well, if you are here, then the thing you should imagine is a rectangular torus. Yeah? So take this as part of the complex plane with the induced complex structure. And now there is an interesting parameter, which is the ratio. And this ratio can degenerate. And that will be quite important for us in a moment that complex curves can degenerate. And if you have a torus that degenerates, then please imagine the torus that it doesn't look anymore like this, but it looks like this. And here is a so-called ordinary double point. Yeah, so that's how we imagine the torus in this situation. What I also want to mention is that this geometry of Teichmüller space is extremely friendly with respect to this geometry of taking the double. So we are not going to use this too explicitly, but it's so nice that I cannot resist to write it on the blackboard. The Teichmüller space of sigma can be identified with, well, not the Teichmüller space of sigma hat. That's obviously, these are two different surfaces. And if this would be disjoint, then this cannot be true, right? But with the fixed point set. So if I take here the fixed point set, and now you can wonder how to deal in this situation with the mapping class group. And you can show that omega sigma can be identified with omega sigma hat. And here I'm taking only those elements that commute with the anticonformal involution. This here is called the relative modular group. Actually, this appeared first in papers of an Italian group, and it played an important role in the development of type 1 theories many, many decades ago. Yeah? So, now for this relative modular group, if we take this here into account, it means that we think of the moduli space as taking Teichmüller space of the double, restricting to the fixed point set, and dividing out by the relative modular group. And that will be a good way to feed this in this geometry in the description of CFT correlators. Okay, that's the end of geometry here. I should emphasize nothing of this is my work. These are classical results, and classical means that sometimes these are results up to the early 2000s. Yeah, so it's good. Now, before I erase and then go to describe the symmetry structures, which is vertex algebras, that's my choice. That's not the only possible choice. Let me ask you whether there are questions. Doesn't seem to be the case, so let me go to vertex algebras. Now, while I'm cleaning the blackboard, vertex algebras are not the only formalization of chiral symmetries. There is a formalism in terms of nets of observable algebras, which is has the advantage that it allows to use results from the operator algebraic theory and from local quantum field theory. But it has the disadvantage that it does not apply to interesting systems like, for example, the CFTs that arise in critical phenomena. It doesn't apply to the CFTs that have been recently discussed in the context of correspondences between superconformal Yang-Mills theories or gauge theories in 3 and 4 dimensions and CFT-like structures either. Here it's on the opposite, it's extremely important that the corresponding structures are non-semi-simple. Yeah? And that's not the case in this operator algebraic context. Good, so this explains my choice. So let me talk about vertex algebras. And before doing this, let me do something very classical. Let me talk about the virasuro algebra. So here, actually, I can again use things from the lecture in the morning. Well, we are interested in conformal symmetries. What we will study are conformal symmetries in infinitesimal way. What are these? Well, John has explained it. These are vector fields. So let me study vector fields on S1. And now choosing as a basis whatever you want, e to the I n phi d phi, or I will prefer equivalently z to the n plus 1 dz, and embed implicitly the circle in a complex plane as the set of points of unit modulus. Well, then everybody here in this audience will be able to compute the commutator between two of these vector fields. Yeah, so, and what you get is n minus m z to the n plus m, and here I should put a plus 1 because by differentiating you lose something, and you get an algebra. Sometimes this algebra is called the Witt algebra. It's a big name. It has been discovered several times. So Witt is the mathematician who also did Poincaré-Birkhoff-Witt. Then it turns out that the Witt algebra doesn't have enough interesting representations. And I'm not going to specify what interesting means, but it turns out that a central extension of the Witt algebra has enough interesting representations. So what is a central extension here? We take not the commutation relations we had earlier, but we can add one term for which we take an element, an additional element that commutes with all Ln, and we add it in a way that it is compatible with Jacobi identities. And this is an exercise. You can do this easily by hand, but really, if you do it by hand, you've done a first computation in the algebra cohomology. So this is really up to something that's under control, the only way you can write additional terms. And this algebra is called the virasuro algebra. And this is a good example that it's good if people do calculations carefully. People did calculations in concrete models, and they found out that commutators didn't work out the way they expected to. They did the calculation over and over. There was always this term, and that was a reason to realize that in interesting models, and that includes the chiral boson, you already have to add this term. Okay, so now, by the way, if you are now looking at representations of this virasuro algebra, then eigenvalues of, if you find an eigenvector in such a representation of L0, the eigenvalue is also called conformal weight. That's jargon, yeah? It's just a different jargon for an eigenvector. In this situation, there is something which is quite convenient, namely, you have infinitely many quantities and you collect them into a generating function, and you are writing down an expression of this type. Now, I should be more careful in principle when I'm working with this type of expressions. So here it is just something which is living in a very formal vector space that I take here, the virasuro algebra, and I take formal power series in z and z to the minus 1. This is not saying a lot. Implicitly, I often mean more, and people in the literature mean more. For example, this will act on certain representations which have the property that locally on every vector, in the action only finitely many terms appear. So these infinite sums are, for this reason, much less dangerous than you might think if you see them for the first time. Good. What I should mention is that this is a convenient way to discover extensions of the virasoro algebra. So there are super extensions for this. So if you are writing a two-component field and you are asking them to describe super derivations of an appropriate super geometry for the circle, then you will find by developing this a Lie super algebra, and this is called the n equal to 1 super virasoro algebra. I'm not going to work with this in this lecture. What I should mention that in classical perturbative string theory, people actually work for the superstring with an n equal to 2 super conformal algebra. So they are adding two more fields here to that field is then also called stress energy tensor, and and on top of this a U1 current. Yeah. So okay. So now I want to, in principle, if I just want to have as a chiral symmetry, the virasuro algebra, I could be happy at this point. Why am I unhappy? I want to have stronger symmetries, which give me stronger constraints. So I need to talk about algebraic structures which comprise more than the virasoro algebra. But I want to build in the structure in a similar way. So it has turned out that the following definition can be used for mathematical work. And I wouldn't say that the definition is beautiful. I wouldn't say that the definition is conceptual, right? And but examples can be constructed and can be investigated. So what are, if I'm looking at a vertex algebra, and notice there is no operator for the moment, then what are the basic data? It should generalize some of this Lie algebra. So what I have here is some complex vector space. I'm not saying that the complex vector space should be graded. This is a graded Lie algebra. I'm not talking about a grading for the moment. It could be a complex supervector space if I want to talk about vertex algebras, but let me drop the super for the moment. Yeah? And there should be a linear map which, well, it should generalize a Lie algebra. You would expect that a Lie bracket goes in this way, but now I want to have a non-trivial dependence on such a formal parameter. So it goes into this vector space with z and z to the minus 1 arbitrary powers. And so what does it mean? If I take a tensor A, tensor B, in V, tensor V, then if I'm evaluating this field map on A tensor B, this is something one frequently also writes as y of A, comma z B. This will be a formal power series in z, so z to the n. Conventionally, in the mathematics literature, people are writing minus n minus 1, but that's a convention here. And here you have certain elements. And this is an infinite series. So one way to think about vertex algebras, which is not helpful, but well-defined, is to say you have here infinitely many products, and they obey a complicated set of generalizations of the Jacobi identity. Actually, in Borchards' papers, which got him the Fields Medal, he's essentially talking about vertex algebras in this way. So at least it's a way to make sure that what you are doing is well-defined. Now, to get closer to ways things are written in the physics literature, it is convenient to regard B as a free variable, to erase it, and to write quantities like this. Well, in the mathematics literature, this is called a vertex operator. Unfortunately, it is almost exactly not what somebody who knows about the theory of a free boson would call a vertex operator. Yeah? But we will see a bit closer what it is. Now, I talked about data. The data are have, of course, to obey certain conditions. So let me talk about the conditions. And the way I think about vertex operator algebras, it's a very, very complicated version of a commutative algebra with one.
So V is a radial vector space?
No.
So what's AN?
This here should take...
on the bottom, I mean the very last line, you have a sum over N of AN Z to the...
Remember that we had this here. Yeah? So it means that for every n, I have a way to take out of an and b to get some other vector in v. Yeah? So if I'm erasing b, then an becomes an endomorphism of v. Yeah? Which given, you give me a b, and we will find some vector in v here for this given n.
How is AN built from A?
For the moment, I said data. So I didn't even give you axioms.
So this is to be specified?
Yes, this is to be specified. Before I can specify it, I should briefly say something about the requirements I have. Yeah? And then the construction of examples is unfortunately complicated. Yeah? So let me say what I require. So what I require is that there is a distinguished element, which is not the zero vector, but nevertheless written in this way, which has the property that if you take this here and you apply it to any vector A, then you're getting A. So this is kind of, now you can rewrite this in terms of the zero vector n, right? This will give you a family of endomorphisms. Almost all of them will be zero, except for one, which reproduces the vector A, which is the identity. Good. So, and then, well, it should be a two-sided unit. So actually, if you apply this to the unit vector, there will be some dependence in Z left, but what we require is that this here is something which is A, and then you have only positive powers. So sometimes this is formulated by saying, if I formally let Z go to zero, which I can do for positive powers, this vanishes. So in the limit Z goes to zero, I'm getting A. But I will never take technically limits. Okay, good. This is identity, and I said that a vertex algebra is a generalization of a commutative algebra, and in fact, any commutative algebra will be, for me, an example of a vertex algebra. This is a bit of a cheat, but it allows me to get examples where I can test general ideas. Yeah, and that's why this definition is technically helpful. Yeah, what is the commutativity requirement? Maybe you would like to say that if you take the commutator of these endomorphisms, right, we agreed that this is a family of endomorphisms, that this is zero. Well, actually what you agree is that this is zero after you fixed a number which depends on V1 and V2, and you multiply this and only then it is zero. This will allow for finite poles in the end. Now, The next thing is you asked me already, it's not graded. Yeah. So actually, let's define a grading. Yeah. So I didn't want to ask for the grading from the beginning. Yeah. So what we do is we define, and this is the notations here. You see, I was sure that I still find typos in my lecture notes, so you will have a revised version, and I take the freedom to note them. Yeah, so because after the lecture I'm unable to remember them all. Okay, so we want to define this, and we want to define this by saying that T, the commutator of T with V, is, well, take this here and take formally a derivative with respect to Z. Yeah, this gives you an expression where, remember, this was a collection of endomorphisms. If we derive them, if you take a derivative, well, we get here some powers down and the degrees shift, and this should match, and moreover, T on our omega should be equal to 0. And it's an exercise that you should check that this is well defined. Yeah? Of course, I can choose on an ordinary finite dimensional commutative algebra, I could simply choose T equal to 0. Yeah? So if there's no explicit dependence on Z. So now you see that there is an apparent mismatch on the blackboard. There is a mismatch because I talked about the virasuro algebra, and then I didn't talk about anything like the virasuro algebra anymore. So let's get the virasuro algebra, and that will lead from vertex algebras to vertex operator algebras. Now, just among us, terminology in this field has been the subject of intense debates. In particular, after a book by Victor Katz has appeared, and there has been even a lawsuit in American courts about this terminology. It wasn't probably appropriate to decide scientific terminology. And so if you see some other use of the words, be careful, read what the authors are explaining. I wouldn't even dare to say that I'm using what is today mainstream terminology. So let's do the next definition. A vertex operator algebra, or a vertex algebra with a conformal structure. Now, two comments. Conformal structure, this is something completely different than the conformal structure on a two-dimensional manifold, obviously. It's a trivial comment, but this is something for the vertex algebra. Second comment, it is structure. One and the same vertex algebra can admit inequivalent such things, which I'm going to define. So what is it? It's the existence of a non-zero vector in our V, which has the property that if I'm looking at the expansion of this here, then I will get coefficients, and if I'm writing them in this way, that they span such that Ln span the virasuro algebra. So you see, we are not saying later that something will be a representation of a vertex algebra, and then the virasoro algebra should somehow act on it. But it will be automatic because everything I have in my vertex algebra will act on it, and in particular the virasoro algebra acts. Now we can come to the grading. So you can take L0, the zero mode of the virasuro algebra, and the zero mode of the virasuro algebra will lead to a direct sum decomposition of the vertex algebra, and in fact it is an eigenspace decomposition. This is different this will be different for representations. In this case, diagonalizability of L0 will not be given. Yeah, so in this case, we have to work with Jordan blocks. And you know, any Jordan blocks gives you just one eigenvalue, eigenvector. Yeah. We have here, so V, N are those V for which the Ln of V has eigenvalue N. And I should give you a word of warning. A word of warning, which is mathematicians will typically write vertex operators in the form Vn z minus n minus 1. Physicists will say if V is in the component to the eigenvalue h, that then they will prefer to write it Vn twiddle z minus n minus h. This is a reason for efficient confusion. And so now I want to give you briefly some examples. And let me explain. So these are examples. And in fact, one of the main sources is infinite Lie algebras. So let's start with something all of you know in one way or the other, with the Heisenberg algebra. So for the Heisenberg algebra, well, that's spanned by generators Bn, n in Z. And again, you could ask this to be abelian, but then you can ask, is there a central extension? Yes, there is a central extension, n plus m comma 0. And now we define a vertex operator algebra structure on what space? Well, let's first take a one-dimensional vector space. Let's take a one-dimensional vector space, and let's turn this into a representation of, well, look, here I can split into positive modes and negative modes. And positive modes, I should say, this is really bigger or equal to 0. Yeah, and I'm asking that Bn is acting by 0 if n is bigger than 0. B0 is also, well, we are on the ground state. So, yeah, so this is a module over this universal enveloping algebra, and I turn it into a module over the Heisenberg algebra simply by taking the induced module. So this is a Fock space. Yeah? And this Fock space, well, now in order to define this map Y, and I should say Y is also called a field state correspondence, well, it's helpful to introduce again such a formal sum, Bn z minus n minus 1. It's clear that each of the Bn's acts on this space, right? So I have such endomorphisms for every n. Yeah? And now I will set that y of b minus 1 of v omega on z at z is just my jz. Yeah, so here, this Fock space, well, it's easy to imagine. At grade 0, there's a single vector. At grade 1, how can I go down to grade 1? I can just use b minus, yeah? So there is a single one. And for this single one at grade minus 1, I take the abelian current. And if I now go further down in a Fock space, well, then I have here creation operators, bn1 up to bnk acting on v omega, and up to normalizations, which are in the lecture notes and irrelevant here. You can now define this as jn minus 1-fold derivative of j up to delta nk minus 1-fold derivative of j. Now, there's something which I do not want to introduce because this is not the main purpose of this talk or the series of talks. There is some way to give this sense, which is called a normal ordering. There are several of these prescriptions, and you take this, and I should have written here, of j, and this will be your define your map y, and this will be an important example of vertex algebras. Yeah. So this is non-trivial and not an exercise to simply say now prove that all the axioms of a vertex algebra are given. Yeah. So b here, that's n1 minus 1.
So n is a positive, right? But you want to apply this to b with negative numbers.
Okay, now I'm getting your question. Yeah. Thanks. Okay, and what I just want to mention here is two important generalizations. The first thing is you can combine this. Well, first of all, here we start with a finite dimensional abelian Lie algebra, which is one-dimensional. We add modes. You can do this with also, you can endow any finite dimensional vector space, obviously, with the structure of an abelian Lie algebra, and then combine several of these systems. And if you're in this situation, you can again construct such a Fock space, and it is very instructive to tensor it with the group algebra of a lattice. So this is a discrete full rank subgroup of V, and in this case, the representation category of this vertex algebra will be fully under control in terms of this lattice data. This is, of course, an important class of examples. And you can replace the also an abelian Lie algebra by a non-abelian Lie algebra. This will be important, and I will use this example then for explaining in an informal way what conformal blocks are. Yeah, so for this reason, let me briefly note this at this point that I can later refer to this. If you are given a Lie algebra, complex Lie algebra, actually finite dimensional, and let's assume that the Lie algebra is reductive. If you don't know what reductive is, take a semi-simple Lie algebra. If you don't want to know what this is, take SL2 and you're not losing anything essential. Yeah, and then we can write down a Lie algebra. I somehow decided here to do it in terms of a basis. So A from 1 is dim G. then you get an infinite dimensional Lie algebra spanned by this A and N in Z. I think everybody already guesses how this infinite dimensional Lie algebra looks before I take a central extension. I take the commutation rules I have in G bar, and then again you can add a central term, and the central term is proportional to the killing form and times n delta n m plus 1. And these are the so-called untwisted affine Lie algebras based on these reductive Lie algebras. So what I would like to emphasize now is the following thing. Here I've again done some central extension. There is one important exercise which has been done more than 35 years ago, right? Suppose I have the Heisenberg Lie algebra and I have the Virasuro Lie algebra. I can form a semi-direct sum of the two. What are the central extensions? And you will say, okay, the Heisenberg Lie algebra has its central extension and the Virasoro algebra has its central extension, but there appears a third degree of freedom. And this third degree of freedom is already a first example which will lead to vertex algebras which are the same but which have inequivalent conformal structures. Yeah? So for those of you who had some class in string theory, probably the other example is a bit more direct. If you have a class in string theory, then you've heard about ghost systems. Yeah, so, and for the ghost systems, or so-called first order systems, well, the situation is the following. You have two fields. Typically they are called B, and with some mode expansion, which I take here in the physics convention, and C, Z to the minus N1 minus H. And we are asking that this is a field of conformal weight lambda or 1 minus lambda respectively. So this is already a family of, this will span a family of CFTs. And if you go to any string theory book, you will find that people compute the stress energy tensor. And the stress energy tensor will have a term which up to a normalization, sorry, this is BDC, has this term, and it has another term, 1 minus lambda BDC. So you see, this is, as a vertex algebra, these are all the same, but there is a family of Virasoro algebras, and the central charge will be 1 minus 3q squared, and q is epsilon minus 1 minus 2 lambda. So you see these are really Virasoro algebras which have inequivalent values for eigenvalues for the central extension. So there is a family of such vertex algebras, and indeed, if I'm not mistaken, for lambda 1/2, and well, there's some tricky thing that you can choose them to be fermionic or bosonic in a super V or A context. Let's choose them fermionic, then this is just a free fermion, a complex free fermion. If you decide to choose this equal to lambda 3/2, then this gives and again fermionic, this gives the super ghosts. So these are these are the ghosts you have to add if you do a superstring construction in which you are gauging one of the supersymmetries, yeah, the worldsheet supersymmetries. Okay, so you see, this is structure. So what is our next step? We have symmetries which generalize conformal symmetries. We study their representations. And we will see that these representations have a lot of structure. Now, why am I so sloppy about many details here? Because in the end, I will not work with the vertex algebras, but I will work with their representation categories. And my goal in this lecture is that you get a feeling why has the representation category of a vertex algebra this and this mathematical structure. Then we will forget the underlying vertex algebra structure and work at a categorical level. And this forgetting is very efficient, yeah? Because I wouldn't be able to work with vertex algebras. I prefer to work with categories in the end, yeah? Good, but let's talk about representations. And let me first, before I write anything, to orient your mind. Think about vertex algebras as generalizations of commutative algebras. If you look at representations of commutative algebras, what do you expect? You can form a tensor product. Yeah? So this will be categories with a tensor product. And this is what I'm trying to explain to you next. And so maybe before I'm explaining this, I should say a word of warning. It's a dirty secret in Lie theory that Lie algebras have way too many representations. Yeah, so already if you look at representations of SL2, they are not classified by spin 0, 1/2, and so on, right? You're talking about finite dimensional representations, or you're talking about unitarizable representations. Now here we don't have unitarizable, we don't have finite dimensional, so we have a problem. What are good categories of representations? And this is a subtle problem in Lie theory, and it's an equally subtle problem in the theory of vertex algebras. And in the course of work over 2.5 decades, people have identified a nice category of representations. The subject is unfortunately extremely technical, which I think means that the right notions haven't yet been found. So the paper, the series of papers which I'm essentially trying to summarize, has a total of 900 pages. This clearly means that the mathematical theory isn't there, yeah? But still, these papers are there. They are correct to the best of our knowledge, and we are going to use them, yeah? So, so the papers I'm talking about is a long series of papers by Huang, Lepofsky, and Zhang. And when I'm mentioning them, I will frequently say HLZ. And they have worked out such a tensor product theory. And we will see what it implies and what it implies at a categorical level. Okay, good. So, maybe first, again, a quick definition. What is a module over a VOA? Well, we have a VOA V and here our map Y. This will be a linear map from V tensor M. So this is M is a vector space. Again, I drop the requirement of a grading into M z to the minus 1. And it has to obey a couple of relations, but in particular, it has to obey a relation you expect for a representation. Now, what do you expect for a representation? Well, let me first write this and then we fill it in together. V1, comma V2. Well, it means acting with V2 and then acting with V1 is the same as multiplying V1 and V2 and then acting. Yeah, that should be a representation. And now here, unfortunately, I have these additional formal variables. Now, we have to insert them accordingly. Imagine that V2 is sitting at Z2, and then V1 is sitting at V1, then here I should act, but I should have only the difference of the two. So these are the definitions of an, this is the essential part of the definition of an action. And now classifying modules over vertex algebras is a hard task. There are techniques. There is, for example, choose algebra, so one can define a finite dimensional quotient of a vertex algebra and then study the representation theory of this. That gives at least insight into the simples. And one can also show that this relation holds for m equal v itself and ym to be equal to y. So what we get is that m is a distinguished representation. So this is a v module. And this is called the vacuum module. And it will be later, I will frequently call it also the monoidal unit. Although at the present moment, I have no reason to call it a monoidal unit. And yeah, now yeah, what should we say here? Then you can study the in V you have a virasuro algebra. We get a virasuro action. In nice classes of representations, this virasoro action decomposes into Jordan blocks of finite size, and you can study the principal values, and that's what's called the conformal weight. They will differ by half integers for a super Lie algebra by integers for a super Lie algebra by half integers. So now I'm coming to a very crucial point, and that's the tensor product. So maybe I do something which probably all of you have seen, which is what is the tensor product of vector spaces. Yeah? And I'm not going to construct it, but I'm characterizing it. So let's first look at this tensor product of vector spaces. Well, what do I have there? I'm given a pair of vector spaces over, well, some field K, and then I'm given a bilinear map to the tensor product, which has the following property, that if you give me any other vector space and you give me any bilinear map, then I should be able to use this distinguished bilinear map kappa to give you here a unique linear map. It was called alpha twiddle, a unique linear map such that this diagram commutes. Well, you see this is bilinear. if I have first a bilinear map and then a linear map, it's still bilinear. This is the universal property which characterizes the tensor product of vector spaces. And it doesn't tell you that the thing exists. And I mean, universal properties are like Christmas presents, yeah? You formulate a wish. If you're formulating the wish concisely enough, there's a single thing which does the job. But you don't know that you get it for Christmas, right? And the construction of the thing can be pretty painful. Yeah? And the same situation is here for tensor products of vertex algebras. For a tensor product of vector spaces, you can ensure their existence, all of you. Yeah? So that's, I have no doubt about this. But for vertex algebras, this will be somewhat different. Okay, so what do we, and a second comment is, this definition is incredibly nice because I have suppressed one thing. If you talk about representations of groups, you will very quickly talk about intertwiners, maps that commute with the representation of groups. I hope you agree that there will be a reasonable definition of a linear map between two morphisms, between two modules over a vertex algebra that commutes with the action. And there's no point to write these things on a blackboard. I could have prepared slides with all these formulae. I don't know whether this would help your understanding. Yeah, so for this, so I have a notion of intertwiners, and for this reason, I have some structure which has representations and intertwiners, so this is a category. Yeah, so we have a category or V-rep, and yeah, what we need to do is we need to define what is a bilinear map for such things, and then we can let the universal property machine run. It tells us that if it exists, there's something unique. The fact that it exists, well, you take the 900 pages of HLZ, you're going to read them until tomorrow, or you trust me, and I haven't read the 900 pages of HLZ either, yeah? But I have collaborators who explained a lot to me, yeah, so? Sorry? Did they read the 900 pages? If I'm asking them, and they are telling me, this is in number 5, around page 35, and it's on page 36, then I don't have a proof, but I have very strong evidence. Yeah, yeah. But you are completely right. I mean, such a theory, which is so fundamental, has to be easier in the end. Yeah, but well, maybe somebody comes up with some bright idea to conceptualize it. It's not completely straightforward. Borchardt has worked on this for a couple of years, and he hasn't come up with anything. So. Okay, but what is nice about this is that we have a tensor product of vector spaces, but we also have a tensor product of linear maps. Yeah, and that comes from the universal property. Yeah, and similarly, we will get also a tensor product of intertwiners of vertex algebras. Yeah, okay. So now I've formulated for you. Enough that you trust me that I should define when is a map from M1 tensor M2 into some third module here. When is this a V bilinear map? Well, now you've seen we have all the time constructed maps which depend on top of this on z and z to the minus 1. Now comes something, and if you look in older literature, you will see that people are trying to formulate bilinear maps in this way. Now comes an important insight. The theory is really getting complete if you are on top of this allowing power series in another variable, which I'm calling log z. Another variable log z means that these two variables are not independent, but rather if I take d of log z, and I took d several times, for example, to define the shift operator, the t, then this should be what everybody expected to be. And this is added here. It gives a nice theory. It comes from inside in the study of concrete, explicit models where people found out that if you study 3-point blocks of certain conformal field theories, logarithmic singularities appear and they make sense. Yeah, so already setting this up in this way is incorporating quite a lot of insight. And now we leave it to the experts to define what V bilinear means. It means that it must be compatible with the action. Yeah, and I have given you a reference where this is written up. And now we can define the tensor product here. And we can say there should be, well, this map here, this is universal. This is called universal in the sense that any bilinear map factorizes through it. So what we claim, what exists, is a universal intertwining operator, which is bilinear, which goes into this tensor product. This is a new tensor product I'm defining. You see, here I defined what is the tensor product over K. Here I want to define a new tensor product over the vertex algebra. Think about it as a generalization of a commutative algebra. These should be a bilinear operator, so I should basically put z and log z here, and such that for any bilinear operator x into any module, and again this comes with z and log z, let me write this informally here, there exists a unique phi. And well, what do HLZ show? They show that such a thing exists in a certain subcategory of representations. They show it in a very roundabout way. And now I have to prove to Kasia that I still read a bit of their work. Yeah, so the way it goes is that they consider the three-point situation on a sphere. They dualize all the representations. They take the three-point situation for the sphere for this. They get a subspace and they dualize again the subspace. This looks very roundabout. In the end, I will hint for you to a categorical reason why it's reasonable to do it this way, but I doubt they did it for this reason. Now, okay, now comes a crucial point. So we have here defined something like a tensor product of representations. And so this category here, which I introduced, VREP, will be much more than a category. It will have a tensor product. You know this from studying representations of finite groups, complex representations of finite groups. You can take a tensor product of two representations, it's again a representations. You know this from coupling spins. Yeah, so we are in such a situation, and in such a situation, you want to have a bit more structure. And I want to convince you that all this structure is, in fact, present. And in order to do this, I have to define for you what the, sorry, I've just to, what a category with a tensor product is. Yeah? And this is the definition of a monoidal category. If you want to, if you're seeing this for the first time, then the very short summary is, I'm going to show you that the category of representations over a vertex algebra behaves pretty much like the category of finite dimensional representations of a finite group. And I will tell you at what point I've cheated here. Okay? So let me write down these definitions, and these will be the input data for our skein theoretic construction later. So so a monoidal category, or C, is a category together with a functor. Well, what do I mean here? If you give me two representations, I get from a pair of representations of the vertex algebra, I get a new one. And I can do this on intertwiners as well. So that's implied by the word functor. That's something which is doing something on representations and intertwiners. Yeah. Now, such a product should be associative. So what do I mean by associative? I could write down that V tensor W, let me just see, well, the notation doesn't really matter too much. Tensor X in this bracketing should be the same as V tensor W tensor X. This is a completely wrong axiom, because two representations are never equal. Two representations are at best isomorphic. Yeah? So I should choose an isomorphism. What is an example where you see that considering two representations to be isomorphic is completely misleading? Take the representations of SL2. Then you know that if you take the spin I representation and the representation on the dual vector space, they are isomorphic. And when I was a student in physics courses, they told me, well, this is isomorphic, but sometimes it's really isomorphic and sometimes it's not so isomorphic. And in one case, you call this real representations, and in the other case, pseudo-real. And they didn't tell isomorphic. They said it's the same, and sometimes it's not so the same. Well, really, you have to keep the isomorphism as a datum. This amounts to a bilinear form, and the bilinear form can be symmetric or not, and that's the Frobenius-Schur indicator. Yeah? So be very careful about keeping these data. So we have additional data here, which are isomorphisms for each pair VWX. Now, these isomorphisms have to be compatible with the intertwiners here in each argument. I'm not going to write this down. If you have seen a bit of category theory, then it means these are natural transformations. But otherwise, you would suspect them to be natural transformations anyhow. And then I have to impose conditions. I have to impose what conditions? Well, you know that the definition of associativity you get in your first year at university is essentially wrong, or it's misleading. Nobody gets up in the morning and says, these two products should be equal in an algebra. But what is really the definition of associativity? Whatever product I take, if I do not change the order and if I change only the bracketing, I get the same result. And then you are proving in order to have this, it's necessary and sufficient to impose this condition. And similarly, we want that if we take a bracketing of n tensorands here and a bracketing of n tensorands here, then no matter how I'm going to change this with the associators, the map that describes the change should always be the same. This is called at the technical level coherence. Now, here for associativity, you're setting down and you're proving that this here is enough. And by the way, that's a small theorem about trees, because any bracketing is a tree or can be represented by a tree. Yeah? So similarly, this here, what you need to, if you are distilling a condition for it, that's also a combinatorial argument. People have done this, obviously, and they find an axiom on these things, which I've written down for you in the lecture notes, and this is called a pentagon axiom. But the essence of it is, if you change the bracketings using these A's, and you do it in no matter what order, you will always get the same comparison isomorphism. That's the essence of the pentagon. Now, the big achievement in these HLZ papers is that they extract from this definition a pentagon. They extract, we have already extracted such a representation, they extract a pentagon. And this is a huge advantage because we can forget all this mess about infinite sums over some formal variable and so on, and we have a very clear categorical structure. Now you're going to blame me. Should I stop then? Yeah? Yeah. Sorry? Yeah, then let me just wrap up things and saying, now you can blame me, why didn't I even take care to write down the pentagon explicitly? Yeah? Because there is a technical result, which means that you can replace the category by an equivalent one in which this thing becomes identities. But this is a small trick which allows me to write down even less definitions. And before I conclude, yeah, and let me say, you're used to have a trivial representation where the tensoring is isomorphic to this here. We have this is the vertex algebra itself, and we have here also such isomorphisms. They have also to obey certain coherence conditions, and HLZ show that they are obeyed. So we are ending up for the representations of symmetry structures with a very nice categorical structure. And we are going to work with this in the remaining 2 lectures more, and I have to wrap up a few things from vertex algebras before.